You know that feeling, right? Sitting in the back of an auto rickshaw, watching the meter take up, and wondering exactly how it knows what to charge you before you even reach your destination. It kind of feels a little bit like magic. But behind that everyday predictability is an invisible mathematical code. A code that governs not just our travel fares, but how our phone batteries drain, how our savings grow, and literally how we predict the future around us.
Welcome to This Explainer. Today, we're cracking that exact code. We're going to take these abstract mathematical equations and transform them into powerful, real-world tools that you can actually visualize and use. We're diving into the mathematics of linear polynomials, stripping away the academic jargon and showing you exactly how they run the engine of our daily lives. Here is our roadmap for today. First, we'll decode algebraic expressions. Second, we look at the linear polynomial itself. Third, we'll explore the input-output machine. Fourth, we'll predict some linear patterns. And finally, we'll wrap up with real-world growth and decay.
Let's jump into Section 1, Decoding Algebraic Expressions, the Language of Math. Okay, let's dive into this with a practical everyday scenario. Imagine a student named Raju hits up a stationery shop. There are sealed red boxes filled with pens and blue boxes filled with pencils. The shop owner tells him, hey, there are 4 pens in every red box and 5 pencils in every blue box. So Raju buys X number of red boxes and Y number of blue boxes, and the owner is nice enough to throw in 3 extra loose pens for free. How do we quickly write down exactly what Raju has? Well, we translate it into the expression 4x plus 5y plus 3. Literally just by taking a physical shopping trip, we've written algebra. Now looking at that expression, the numbers 4 and 5 serve a very specific purpose. They're what we call coefficients. A coefficient is simply the number securely attached to a variable, telling us exactly how many of that particular item we have. In Raju's case, the 4 tells us there are precisely 4 pens bundled into each red X box, and the 5 tells us there are 5 pencils in each blue Y box. They're essentially multipliers. But wait, what about those 3 extra free pens Raju got? That number is completely independent of how many boxes he buys. Whether he grabs 1 box or 100 boxes, he still gets exactly 3 free pens. In math, this is called a constant. It's a fixed value in an expression that absolutely does not change. The variables x and y can shift around all day long, but that constant of 3 remains stubbornly, reliably the same. Moving right along to Section 2, the linear polynomial, the core engine. To truly understand what makes a polynomial linear, we first need to look at its degree. The degree is simply the highest power of a variable within the polynomial. Think of the degree as the defining characteristic that categorizes exactly how a polynomial is going to behave when we start plugging numbers into it. It dictates the shape of its graph and the whole nature of its growth. This is where we draw the line in the sand. On the right, you've got a quadratic polynomial, where the highest power is a 2, like x squared. Those create curves and accelerating changes. But our focus today is strictly on the left side, the linear polynomial, which has a degree of 1. Expressions like 3z plus 7. The variable z has an invisible power of 1. Because the degree is 1, these polynomials represent constant, steady, predictable change. No sudden curves, no exponential explosions, just a perfectly straight mathematical line. Which brings us to Section 3, the input-output machine. Math in motion. And this brilliantly illustrates the concept. Think of a linear polynomial, like y equals 2x plus 3, as a literal mechanical machine. You drop an input value, let's say an x value of 4, into the top of the machine. The machine grabs it, multiplies it by 2, adds 3, and spits out an output of 11. It takes raw material, processes it at a constant rate, and hands you a finished product. Every single time. Let's put the machine to the test. Take a brief second right now. If our input is an x of -6, what happens inside our 2x plus 3 machine? Well, the machine multiplies -6 by 2 to get -12, then it adds 3. The output perfectly reliably emerges as -9. The machine literally never fails. Now, we can use this machine to solve actual problems. Though, let's be real, math textbooks do love giving us these oddly specific, perfectly proportional scenarios. Like a farmer who meticulously cuts a 300-foot fence into 2 pieces where the longer piece is exactly 4 times as long as the shorter piece. I mean, who has the time, right? But it works. If the short piece is x, the long piece is 4x. The linear equation x plus 4x equals 300 perfectly models the scenario, allowing us to find that x is exactly 60. All right, section 4, predicting linear patterns, seeing the matrix. Let's visualize a growing pattern of square tiles. Stage 1 kicks off with a single tile. Stage 2 bumps up to 3 tiles. Stage 3 has 5, and Stage 4 has 7. If you look closely at how this visually grows, you can see that we're simply adding exactly 2 new tiles to the top and right sides at every single stage. It's a steady, constant addition. Let's map that data out and see how it builds. From stage 1 through stage 7, the number of tiles goes 1, 3, 5, 7, 9, 11, 13. The math perfectly backs up our visual observation here. The difference between consecutive terms is consistently, undeniably exactly 2. And because that difference is constant, we know with absolute certainty that we are dealing with a linear relationship. Because it is a linear relationship, we can lock in a general rule for this pattern, which is 2n minus 1, where n is the stage number. Now, this is practically a superpower. We don't need to draw out the tiles anymore to know what comes next. I challenge you right now, using 2n minus 1, mentally calculate the number of tiles in the 15th stage. Did you get it? 2 times 15 is 30, minus 1 is 29. Boom! You've just predicted the future of this pattern perfectly. Finally, let's hit section 5, real-world growth and decay, predicting the future. So the absolutely crucial point here is this. Whenever quantities in the real world change by a constant, steady amount over equal intervals of time or distance, they are governed by linear polynomials. If the quantity is steadily increasing, you've got linear growth. If the quantity is steadily decreasing, dropping by the exact same amount each interval, it's linear decay. They're basically just 2 sides of the same mathematical coin. Let's look at linear growth in the wild. Remember our auto rickshaw from the start? Consider a fare that starts at 25 rupees for the first 2 kilometers, then increases by 15 rupees for every kilometer after. The math simplifies brilliantly into the linear polynomial 15n minus 5. It's a perfect input-output machine. If you travel 10 kilometers, you just input 10 for n. 15 times 10 is 150, minus 5 is 145 rupees. There's no magic involved, just constant linear accumulation. Now, what's really interesting about this is how linear decay hits our wallets. Take that brand new mobile phone you just bought for 10,000 rupees. Its value might decrease by 800 rupees every single year. The linear polynomial for its value over time, t, is simply 10,000 minus 800t. By year 3, that phone is predictably worth 7,600 rupees. It is mathematically perfect, relentless decay. The exact same rule applies to a water tank draining uniformly in the summer or steadily spending your pocket money each week. We've seen how linear polynomials decode everything from simple shopping trips and tile patterns to auto rickshaw fares and phone depreciation. So I want to leave you with a final thought to reflect on today. We all have habits that accumulate or deplete over time. If your own daily life was modeled by a linear polynomial right now, whether it's your savings account, your learning, or your daily energy levels, what would your constant rate of change be? Are you currently in a state of linear growth or linear decay? Definitely something to think about as you go through the rest of your day. Thanks for joining me for this explainer, and keep looking for the invisible code all around you.